All right, in this video we're going to look at limits, rates of change, and tangent lines. This will be a basic introduction here. So we're going to start with the concept of average velocity. So just broadly speaking, calculus is called the math of change. It allows us to measure and calculate things about objects that change or quantities that change over time. So the first application that we're going to use has to do with speed, but more technically we're actually going to look at velocity. So velocity is considered speed with direction. So if you are moving maybe up or to the right, that would generally be considered a positive direction. Or if you're moving down or to the left, that's usually considered a negative direction. Okay, so for example, if a car drives 120 miles in 2 hours, what was the velocity of the car? Well, if you travel a total of 120 miles and it takes you 2 hours to do that, on average you're traveling 60 miles per hour. Okay, but that's really the car's average velocity, not its velocity at every second among its trip. You know, when the car starts out, it's going to be going 0 and it's going to slowly speed up. Maybe the speed limit is 70, 75, depending on where you're at. And then maybe the speed varies, maybe they hit the brakes, they hit the gas some. You know, the speed's constantly changing. Okay, so on average, the car would have traveled about 60 miles an hour. But what we're interested in calculus is looking at instantaneous velocity instead. That's what we're going to move towards. So over the 2-hour trip, again, everything changes. Now, average velocity is defined as your change in your distance divided by the change in the time that has elapsed, okay, since your counter is going. Now, we can't define instantaneous velocity as a ratio like this, okay, because if you are looking at instantaneous velocity, that's in a single, split second, right? It's what you see when you look at your speedometer as you're driving. The change in time that elapses in that single moment is 0. So the change in time, or the time elapsed in a moment, a single quick little moment, is, at least theoretically, is 0. Okay, so we can't use this change in distance over change in time formula to find instantaneous velocity. Okay, so we're going to develop the techniques to do that, to find instantaneous velocity next. But really what we're doing is developing techniques that can be used to find the rate of change of any changing quantity, whether that be distance or whether maybe it is, it could be anything else, right? Like you could look at, in business calculus, often students look at the rate of change and just generally speaking in the amount of money in some account, or maybe like you're looking at a stock and its growth, how fast is the stock growing, or how fast did it fall. Okay, it has to do with the rate of change. That's what we're going to find. It's not just rate of change of position or distance, but rate of change of any quantity. In, say, physics or in engineering, you might find the rate of change of volume, of something, maybe volume of water in a container. Okay, you can think about things that move, things that change. We're going to find how fast do those things change. Okay, that's what we're going to find next in calculus. There's a number of other examples I'm sure you guys could come up with. All right, a common symbol that I'm going to refer to here is delta. That commonly represents change in. Okay, so let's go back to the distance and speed problem. So I'm going to let position or distance traveled be denoted by S, and that's going to be a function of time. So S of t is a position function. It tells us the distance from some origin. And we're going to let t0 and t1 be an interval over time. Okay, so t0 is our starting time, t1 is our ending time. So the average velocity of an object over that time interval would be given by the change in distance over the change in time. And change in distance would be distance at the second time, so s of t1, minus the distance at the initial time, that's the total change in distance over that time span, divided by the actual change in distance, or actual change in time, t1 minus t0. Okay, for example, if a car sits at a red light and then the light turns green and the car speeds up to enter a ramp, or speeds up on the ramp to enter I-35. 3 seconds after the light turns, the car has traveled 150 feet. 5 seconds after the light turns, it has traveled 300 feet from its initial position. What was the average speed of the car between 3 and 5 seconds after the light turn? Well, we can calculate the change in the distance over that 2-second span, and we can also calculate the change in time because that's a 2-second span. So the average speed, technically I should say velocity, but I'm not going to worry about direction in this particular problem. So the average speed would be the ending position, s of 5, minus the beginning position, s of 3, over ending time minus beginning time. So position at 5 seconds was 300 feet from the origin or starting point. Position at 3 seconds was 150 feet. That's over 2, so we get 150 over 2, or 75. Units are important here. Feet per second would be the average speed over that 2-second span. All right, in this next problem, we have Galileo discovered that in the late 16th century, that when an object is dropped from rest and allowed to free fall, it will fall a distance proportional to the square of the time that it has been falling if you ignore air resistance. So if you measure distance in meters and time in seconds, then the distance fallen in meters, which is y, after t seconds is given by 4.9 t squared. And that's just a constant, that's the approximated version, 4.9, but it's pretty close. It's commonly used. So if you're in meters, the distance that something has fallen, if you drop it, the distance it will travel after t seconds is given by y equals 4.9 t squared. What we're going to do is estimate the instantaneous velocity of the object 3.5 seconds after it is dropped by calculating the average velocity of the object over smaller and smaller time intervals. Okay, so we're going to start with a time interval of, let's see, we want to approximate the instantaneous velocity at 3.5 seconds after it's dropped. All right, there's 2 ways to do this. There's time intervals to the left of 3.5, and then there are time intervals to the right of 3.5. You could also include 3.5 in the middle of your time interval, which might give you a more precise answer, but I want to do this in such a way that we can, develop a method, right, about how to do this better without having to do it numerically. Okay, so if here's 3.5, first I'm going to go to the left side of 3.5 for my intervals. So let's take a time interval of, how about 3 to 3.5. So that's a 1/2 second interval. Okay, so the average velocity over that time is its change in distance over change in time. So change in distance, we're going to use that to find it. I'm going to write out my work on this first one and then not on the next ones. It's going to be 4.9 times 3.5 squared minus 4.9 times 3 squared. That's the change in the distance over that time interval. And this is happening over a time span of 1/2 seconds. So we're going to need a little calculator here. Okay, so we are going to do, let's see, 3.5 squared. Actually, you know what, let's first do this. 3 squared is 9 times 4.9 is minus 44.1. So, okay, so we're going to have the first term minus 44.1. We'll just remember it and come back. Okay, so then we're going to do 4.9. No, we're going to do 3.5 squared. And then times 4.9. Okay, so we're going to do that minus 44.1. It's 15.925 divided by a half, 31.85. And I want to double check myself on that. Let's make sure it was right. 9 times 4.9 is, yeah, 44.1. Okay. And the units on the average velocity here are in meters per second. Let's just put that up here since we're going to be short on space down here. Okay, so from the time interval of 3 seconds after the object is dropped, that's right here, to 3.5 seconds, that's right here in the middle, okay, the average speed is 31.85 meters per second. So we need to get a better approximation, so we could take a smaller time interval. Right, we could go from maybe 3.4 to 3.5. Okay, so if we do that, let's see, plugging in 3.5, we'll have 3.5 squared times 4.9. It's the same as it was in the first, with the first set I did, so 60.025. That's plugging in the 3.5 squared and times the 4.9. Then we're going to do minus 3.4 squared times 4.9. It's 56.644. 644. That time interval only has a length of 0.1, so it's a bit of a shorter time interval. So let's go over here and calculate that. So we've got 60.025 minus 56.644. We're going to divide that by 0.1. So over that time interval, it's going a little bit faster, which makes sense because it's falling. It's getting faster as it falls. So 33.81 feet per second, or meters per second over that time interval. All right, obviously to get a better approximation, we can do a smaller time interval. So let's go with 3.49 to 3.5 seconds. That's a time interval of 1/100th of a second. When we plug in 3.5, we're still going to get the same thing, 60.025. The time interval is 0.01 seconds. All right, so we need to plug in 3.49. So I'm going to do 3.49 squared times 4.9 gives me 59.68249. Up right here, 59.68429. Okay, going back to the calculator here. What we can actually do is make that negative, and then I'm going to add 60.025 and divide that by 0.01. Okay, 34.251 if you round, 34.251. So 34.251, yeah. Okay, so it looks like maybe it's going to approach 34.25. It's hard to say. You can get an even closer approximation. Oops. So let's do that. Let's go from 3.499 to 3.5. Plugging in 3.5, we'll have 60.025. Okay, when I plug in 3.499 right there, we're going to have 3.499 squared times 4.9 gives me 59.99. I'm just going to round here for the moment for what I write. I'm not actually going to round for my approximation though. So 59.99 here. It's going to be over 1,000th of a second. Okay, so let's go back to the calculator. Let's make that number negative, and then we'll add 60.025. We're going to divide that by 0.001 to get 34.2951. 34.2951. Okay, well, that's all good, and that's probably very close to the exact instantaneous velocity at 3.5 seconds. The way we could get a better approximation is to also approach 3.5 from the left. So take the time interval, on the right, to the right side of 3.5. So you could find the average velocity over the time interval from 3.5 seconds after it's dropped to, say, 4 seconds after it's dropped. Okay, see where this is going? So we'll want to plug in 4 first. So 4 squared is 16 times 4.9. We'll get 78.4. That's plugging in 4 in there. Minus, now let's plug in 3.5. Oh, we already did. When we plug in 3.5, we get 60.025. This time interval is a span of a half a second. So let's see what that comes to. So we've got 78.4 minus 60.025. We're going to divide that by 0.5 to get 36.75. Okay, so we would expect it to be a faster speed than over here because it has fallen further. Right, it's been falling for longer. Okay, let's make our time interval shorter. So let's go from 3.5 to 3.6 seconds. So we need to plug in 3.6 first. So 3.6 squared times 4.9 is 63.504. That's minus what we get when we plug in 3.5 squared, which we already know is 60.025. And this is a time interval of 1/10 of a second, so we'll divide by 0.1. So we've got that, then minus 60.025 gives us that, divided by 0.1 gives us 34.79. Okay. So these numbers are approaching 34 point something. Okay, we'll get a close idea here. Let's go from 3.5 to 3.51. Let's try that. So when we plug in 3.51, we've got 3.51 squared times 4.9. Okay, 60.36. On paper, I'm just going to round it to 368, but not in the calculator. 60.368 minus the 60.025 divided by a 1/100th of a second. Let's see what that comes to. Okay, so we've got that number, then minus 60.025 divided by 0.01 becomes 34.349. Okay, and let's just finish this up. Let's get a little bit closer. Let's go from 3.5 seconds to 3.501 seconds, and we're going to calculate the average velocity over that 1,000th of a second there that elapses. So we need to plug in 3.501. So 3.501 squared times 4.9 gives me 60.059 roughly. 60.059. I'm going to subtract 60.025 from that and divide by 1,000th of a second. Let's see what we get. So minus 60.025. then divided by 0.001, get 34.3049. 34.3049. So if you have to approximate and round here, which is really what we're doing, looks like these numbers are approaching 34.3. So I'm going to say the exact instantaneous velocity of the object 3.5 seconds after it has fallen is about 34.3 meters per second. Okay, that's a pretty close approximation. I think it's pretty accurate, at least to the first decimal. Beyond that, there could be some little details there. But if there's no air resistance, right, that's how fast the object would be falling 3.5 seconds after it's dropped. Okay, so that is how you find instantaneous velocity numerically. And that's not a way we're really going to do it for practical purposes. This is really just to illustrate and to help you to understand what we're doing a little bit better. Now you could also find instantaneous velocity graphically. Okay, for example, if you have a rock, let's say, that is launched vertically upwards from the ground with an initial velocity of 96 feet per second, so neglecting air resistance, right? From physics we know then, now we're in feet, so that the height of the rock t seconds after it's launched is given by s of t equals negative 16t squared plus 96t, where the height s is measured in feet with s equals 0 corresponding to the ground. We want to find the average velocity of the rock between these following time intervals, and then we're going to look at it graphically, and we're going to estimate the instantaneous velocity of the rock just 1 second after it has been launched upward. Okay, so first we're going to plug in some simple numbers. We're going to find the average velocity over the interval from 1 second after it's launched to 3 seconds after it's launched. Okay, which is still change in distance or change in position over change in time. So it's position at 3 seconds. You can plug in 3 and calculate s of 3, or you can just read it off this graph right here. The height at 3 seconds, if you plug in 3 here, you're going to get is 144. So we get 144 minus the height at 1 second after it's launched is 80 all over 2. So let's see, 144 minus 80, that's going to be 64 divided by 2, or about 32 feet per second is the average speed. Now it's going to be going faster than that 1 second after it's launched, and then it's going up, the rock is going up, so it's slowing down. Okay, so if we calculate the average velocity from 1 to 2 seconds, I think we'll get a faster average speed over that time interval. So that average velocity would be s of 2 minus s of 1 over the time interval, 2 minus 1. S of 2, we can just read off the graph here, is 128. S of 1 is 80. And we're going to divide by 1. So here we're only getting 48 feet per second. Okay, so it is getting faster because the instantaneous speed at 1 second is going to be faster than it is at 2 seconds, which you can clearly see here. Okay, so the instantaneous velocity of the rock 1 second after it's launched is going to be a little bit faster. Now notice what this corresponds to graphically. Okay, I have really just computed change in y on this graph. That's 144 minus 80. That's that change in y value right there, which is 64. And this is the change in x between these 2 points. That's that distance on the x-axis. Okay, same thing here. The change in the y value is 48. The change in the x is 41. Change in y over change in x between 2 points is actually slope. Okay, so the average velocity is equaling the slope of what's called the secant line. A secant line is a line that goes through 2 points. So it's the slope of the secant line that's through the 2 points. Same thing here, that's the slope of that secant line. But as you move this second point towards the first point, you no longer have a secant line. As that second point becomes closer and closer and closer to the first point, you have what's called a tangent line. Okay, and I'm going to open up a program here where I can actually move this line a little bit here. All right, so this is actually not a visual representation of the line. However, it is the same numbers here. You can see from t equals 1 to t equals 2, the average velocity is 48 feet per second. And if we make that time interval smaller and make it closer and closer to 1 second, you can see what happens to these numbers here. Okay, if the time span of 0.1 seconds, the average speed over 0.1 seconds is 62.4. If you look at 1/100th of a second, 63.84. 1/1000th of a second, 63.984. You can see that the average velocity is approaching 64 feet per second. Okay, so the average velocities are approaching 64 feet per second, and that is going to be the instantaneous velocity of the object that's been launched. Okay, exactly 1 second after it's been launched. Here's another visual, although it doesn't get too close. Let's see, from 1 to 2, that's what we have. And I wish I could make it slide in right where you could see, but I can't quite do that. Anyways, hopefully you can visually see that if that point moves, the second point moves towards the first, in the end you're really only touching at one point. Okay, so we've learned graphically that the instantaneous velocity at 1 second is 64 feet per second, and that still corresponds to slope. Okay, the slope of that line right there, it's not a secant line, but the slope of that tangent line is 64. Well, the slope doesn't have units, so it's just 64. The instantaneous velocity of the rock after 1 second is 64 feet per second. So what we're going to do in calculus is learn better ways, not numerically and graphically, but an algebraic way to find that exact slope of that tangent line, which would correspond to the instantaneous velocity of moving objects. Okay, so let's look briefly at what is a tangent line and what's not. Okay, here's 2 points P and Q. The goal is to find the tangent line at P, and if you move your second point Q closer and closer and closer to P, you can see those tangent lines, how the slopes of those tangent lines get closer and closer to the slope of the tangent line at P. Okay, here's a diagram here. This one is not a tangent line. This is not a tangent line. They just cut through the graph. Now at this one, the slope of the line does approximate the slope of the function at that point, so that would be considered a tangent line. Now T2 is a little bit difficult. It does cross, however, it's still a tangent line because the slope of the line approximates the slope of the function at that point. So what you want to do is approximate the slope of the curvature of the function to have a tangent line. So all of those are in fact tangent lines. And that's it for this section.